is true. With another difference, there are two kinds of matter, which we can call positive and negative. Like kinds repel and unlike kinds attract. Unlike gravity, where there is only attraction. What would happen? A bunch of positives would repel with an enormous force and spread out in all directions. And a bunch of negatives would do the same. But an evenly mixed bunch of positives and negatives would do something completely different. The opposite pieces would be pulled together by the enormous attractions. The net result would be that the terrific forces would balance themselves out almost perfectly by forming tight, fine mixtures of positive and the negative. And between two separate bunches of such mixtures, there will be practically no attraction or repulsion at all. There is such a force, the electrical force. And all matter is a mixture of both positive protons and negative electrons, which are attracting and repelling with this great force. Wow. Now, I actually wrote down about 5 or 6 ways to deduce charges and forces between them, thinking about what would be the best way to start this topic. And then I read Feynman's version of it. And I realized that there probably isn't a better way to introduce this new idea, called electric force, better than he has. If you read those lines, you begin to notice the amount of simplicity in them really hides the depth to which they're going. And we're going to spend the next some time really taking those sentences and unwrapping them to understand really what he tries to tell in those very few lines. So, what's the basic idea? Just like mass is a property of matter, there's one more that we call charge. Except that charge comes in 2 types. One we call positive and the other we call negative. Now what's interesting is that in the case of mass, all mass attracts each other. We call it gravity. But in the case of charge, like ones, in other words positives and positives, and negatives, want to get as far away from each other as possible. But the unlike ones, positives and negatives, want to be as close to each other as possible. They attract, we call it. Now the interesting thing is that this attraction or repulsion actually reduces as these charges get further and further away. But why is there a charge? Why do particles that are charged or bodies that are charged attract or repel each other? Now these are questions we may not have meaningful answers for. But what you need to know to really appreciate what's happening in the next couple of chapters called electrostatics is just this question, answer to this question, which is how much force exists between charged bodies, how it changes with distance, and what that leads to in the universe around us. And that's what you will learn as we go forward. Right? Yeah? Hey, we haven't spoken about two really important and weird ideas about charges, right? Let's do this. You're all familiar with the glass rod, and you take this glass rod and rub it with what we call a silk cloth. And you've been told that if you rub the glass rod with silk, you're going to get charges onto one of them or both of them. And this is going to start being able to attract pieces of paper. But when I was learning this, I had a question. Okay, I was wondering, how does a charged glass rod look any different from an uncharged one? And what does rubbing have to do with charging? Well, these are questions that we want to think about. But to answer the question about what is really different about this glass rod now, and what is different about it after it is charged, we cannot do it by looking at it at this level, because we have to go to a level that's deeper than our eyes can ever see. The atomic level. So for the atomic model, the basic thing you have to know is that all matter is made up of little indivisible pieces called atoms, which have constituents called the nucleus in the center, and electrons that are going around it. Yeah, I know that sentence is very, very weird, it's self-contradictory. How can an atom be indivisible if it has pieces inside? See, we thought it was indivisible, okay? When we first found the atom, we thought it was indivisible. We didn't know anything inside it, what was inside it. And then we found out. We couldn't change the name again, so we just have the name. The word atom does mean indivisible. But now we know what's inside. And what we do know now is that, almost now, for some time ago, we know even more right now, but we're not going to tell you that. What you need to know at this point is that there's a nucleus in the center which is positively charged, which contains protons and neutrons. And there's something around it that keeps going around in some sense. We call them electrons, and they are negatively charged. So in the nucleus, the protons are the ones that are positively charged, and the neutrons are neutral. So it's these protons and electrons that mostly create charge phenomenon around us. They are the ones that have the charge that make bodies get charged or lose charge. So it is this electrical force between the positively charged protons and negatively charged electrons that's keeping the electron from going away from this nucleus. That's what keeps the atom intact. Now you are asking, why couldn't the electron just go inside because they're too attracted and can just end up there? That's a great question. There are some reasons why that doesn't happen. Yeah, quantum reasons, let's call them. So, but the electron's going to be there, not any closer, but it doesn't go away because the electrical forces keep them there. Now, even though the charge on these two experimentally has been found to be almost equal. Why I'm saying almost is because within our error of measurement, they're equal. So we're very, very confident that the charges are equal, but the masses are very different. The proton is about 1,800 times more massive than the electron. The neutron, of course, is a very similar mass to the proton, slightly higher mass. So if you observe this, even though an atom is, large, most of its mass, 99% of it, more than that, is concentrated in the nucleus. And it's much smaller. The nucleus is really, really small in comparison to the atom size. So if you imagine the atom to be about a football field size, then the nucleus will only be a football size. So this should strike you as odd because most of what we see around is made up of atoms, and most of the atom is empty space. And the most of the universe itself is empty space. So even though in our locality it doesn't come across, right, we see most of the things being solid around us. The only reason we see it that way is because we've evolved to see it that way. If you really look inside, it's all empty. But there are other fundamental particles as well, right? But we're not talking about them. We're sticking to protons, electrons, and neutrons because that'll do the job for now. So now that you do know what happens at the atomic level, you're ready to understand what we mean when we say the body is charged in the real world. Now, any typical body that you take is not made up of a few atoms, but billions of them. Now, to get an idea for this, take a 70 kg human being, and you find that he typically has about 7 into 10 to the power of 27 atoms. That's about 7 billion atoms in his body. About 62% of them are hydrogen atoms, I think, and about 24% are oxygen atoms, 10% are around 10 to 12% are carbon atoms, 1% nitrogen, I think, and the rest are many kinds of atoms, many elements. So all these atoms together constitute the human being, and even if a small fraction of them are not neutral, in other words, do not have the same number of electrons as protons, then we say the human being is charged. Same rule applies for a glass rod or a silk cloth. Now you're asking, a small fraction of charge, atoms not having the same number of electrons and protons, right? How much does it matter? To get an idea for this, let's imagine two humans standing at arm's length, each of whom have 1% more electrons than protons. So they're both negatively charged, so you expect them to feel repulsion, right? Now, how much repulsion do you think is going to exist over there? Yeah? In the next video, you can learn how to calculate this exactly, but to get an idea for how much it is, let's equate it to something that's much more familiar. Yeah? How much force do you require to lift something on the earth? You know that heavier things are harder to lift. You need more force to lift them. So do you think that this force would be as much as the force required to lift the entire Empire State Building? This example that Feynman uses to really get you to imagine how strong this force really is. It's not. It's more than that. Is it as much as the force required to lift Mount Everest? Well, that's a huge amount of force. It's more than even that. It is close to the amount of force required to lift a weight equivalent to that of the entire Earth. The mass of the Earth, to lift that, the force required is what? Will be close to the force between two human beings who just have 1% more electrons than protons. That's to get a sense of how strong this force is. Now, a natural question though is, if this force is so strong, then why don't we see it more often around us? Why is our world dominated by this seemingly weak force of gravity? That's a great question to hold on to, and we'll talk about it in the next video. And now with all of this, we're ready to learn the first of the two weird and interesting properties that these charges have. And that is that the total amount of charge in a closed system is conserved. In other words, the net charge is conserved. So in this sense, it's something like energy. It can neither be created nor be destroyed, but only be transferred from one body to another. Even in high energy scenarios, where pairs of particles are created and sometimes particles are destroyed, this property still holds. So we haven't yet found a scenario where this law, the law of conservation of charge, is broken. Now, one of the most important things to remember about the law